Welcome friends to my YouTube channel. Now on last lecture I have told about the rotational kinetic energy and angular momentum of a rigid body in terms of principal moments of inertia. Okay. And with that I have finished the fourth chapter, that is the rigid body dynamics. Okay. In this lecture I shall going to start a new chapter, that is this is rotating frame of references. Rotating frame of references. Okay. From today's lecture I shall going to discuss this chapter. Now here at first we have to find out what are the different types of frames that exist. Okay. So we all know that one frame is known as the inertial and another is non-inertial. Let us try to understand these frames. There are two types of frames, that is one is inertial and another is non-inertial. Okay. Now what is inertial frame? That you all know that the frame in which Newton's laws of motion holds good is called inertial frame of references. Okay. Newton's laws of motion holds good. Okay, that means a body, as long as the external force acting on a body, okay, it is at rest or it can continue its uniform motion. Okay, so in inertial frame, Newton's law of motion holds good. Okay. Now here one thing is important, that any frame that is moving with a uniform velocity with respect to an inertial frame is also an inertial. Okay. Suppose there is a inertial frame S and another frame S dash is moving with respect to S with a constant velocity, say V, then S dash is also an inertial. Okay. So any frame that is moving with constant velocity relative to an inertial frame will also be inertial. So any frame that moves with a constant velocity relative to a inertial frame is also inertial. Okay, so this is the most important thing, that any frame that is moving with a constant velocity with respect to an inertial frame is also an inertial. And another thing, so if there is a velocity is constant, then acceleration is what? V is constant, that means acceleration is 0. So for this reason this type of frames are known as non-accelerated frames. Okay, non-accelerated frame of references. Okay, that is uniform velocity means acceleration is 0. So that means these frames have no acceleration and these are known as non-accelerated frame of references. Okay. Now what are the examples of inertial frame? the best example you can say that the frames in intergalactic space. Okay, all frames in intergalactic space are inertial. This is the common example. Okay, that is, the frames in the intergalactic space are called inertial frame of references. Okay, now the second thing is the non-inertial frames. Non-inertial frames. The frames that have an acceleration with respect to an inertial frame are called non-inertial frames. Okay, that is, these frames have an acceleration with respect to an inertial frame. So these frames have an acceleration relative to a inertial frame. So these are called accelerated frame of references. Accelerated frame of references. Okay, the common example you can take, the earth is a non-inertial frame. The common example is earth. Why earth is a non-inertial frame, that we explain. Okay, because we all know that earth is rotating around the sun. Okay, and there is a centrifugal or centripetal acceleration. Okay, now the earth is rotating around the sun in 365 days, and besides this it also rotates about its own axis due to spin. So earth is rotating around the sun and the distance is then this. Okay, so what will be the, and the time period is what, 365 into 24 into this in second. So what will be the orbital velocity, that is 2 pi r by t. Okay, so 2 into 3.14 into this 15 into 10 to the power 10 by t, 365 into 24 into. Now what will be the centripetal acceleration, that we all know, centripetal acceleration, or you can say the centrifugal. More commonly, since we are talking about the rotating frame of reference, you can say centrifugal acceleration is what, that is v square by r. So if we substitute the value of this value v and take r, then the result is approximately 6 into 10 to the power minus 3 meter per second square. So we see that earth has a centrifugal acceleration due to the own motion around the orbit. Okay, so that's why earth is a non-inertial frame of references. Okay, so we take the example of earth. Now next thing that we have to introduce, that is Galilean transformation. Galilean transformation. That is, what is it? That these are the set of equations that connects the position vectors of a particle in two different inertial frames. Okay, that is, suppose there is a inertial frame S and another frame S dash is moving with a constant velocity with respect to S, so it is also an inertial. Okay, so at any instant, if the position coordinates of an event, say P, at x is x, y, z, t, and that at h dash is x dash, y dash, z dash, t dash, then we can connect these two coordinates by a set of equations that are known as the Galilean transformation equations. Okay, S is the inertial frame and another frame S dash is moving with a constant velocity v with respect to S frame, so S dash is also an inertial. So if at any instant t the position coordinates and time coordinates of an event, say P at S frame is this and that at S dash frame are this, then we can connect these two equations by using Galilean transformation equations. Okay, so a set of equations that connect the position vectors of a particle in two inertial frames are called Galilean transformation equations. Okay, so what are the equations? Let us try to understand this. Now what are the equations? Let us try to understand this. Now suppose this is a frame, S frame, and say this is a S dash frame. This is O dash, this is S frame and this is S dash frame. Say this is X and X dash, this is Y dash, Z dash. Now here we consider the case that the frame S dash is moving with a constant velocity v with respect to S frame. That means S dash is also an inertial. Okay, so and we also assume that the centers of two frames coincides. That means at t equal to t dash equal to 0, O and O dash coincides. We have to assume this. Okay, both the frames coincides at the start. That means when t dash equal to 0, O and O dash are the same point. So what happened after a time t? So say this is X and this is X dash and this is V. So after a time t, say the frame H dash moves here, so we can clearly write if this is X, so this is equals to this, that means Vt plus this X dash. So what will be my X dash? X dash equal to X minus Vt. And since the motion only takes place along x-axis, y and z coordinate remains unchanged. That means y dash equal to y, z dash equal to z. And also we assume t equal to t dash. Remember that here we assume the universal nature of time. That means a clock for an observer in S frame, a clock measures the same time as another clock measures in S dash frame. Both the times are equal. Okay, if a clock measures a particular time in S frame, then another clock in S dash frame will also measure the same time. That's why we take this, that is universal nature of time, that is time is absolute. Okay, so these are known as the Galilean transformation equation, provided the frame S dash is moving with a constant velocity v with respect to S frame in positive x direction. Okay, so this is the simple equation. Okay, just I write it. When H dash frame is moving with a constant velocity v relative to S frame in plus x direction, then what we can write? This y dash equal to y, z dash equal to z, t dash equal to t. Here we assume two things, that is time is absolute, that is universal nature of time, and second thing, mass is same for all observers, that is mass also absolute. Okay, so these are the Galilean transformation equations. So in our next class we will discuss few important issues, that is about Galilean invariance. What is Galilean invariance, that I will discuss in my next class. So if you don't subscribe my channel, then kindly subscribe it to get latest videos. Okay, thank you.